Welcome to another video on Honors Pre-Calculus. We're doing matrices and their operations today. So a matrix is basically, you think of it like a spreadsheet. It's basically a 2 by 2, for example, set of values, and it's two-dimensional. So in this case, we said 2 by 2, so it can be something like 0, 1, 9, -5. And the rows are the horizontal and the columns are the vertical. The dimensions is basically row by column. So in this case, it's 2 by 2. That's not such a great example because both the row and the column are 2. But if we had something like 0, 1, 9, -5, 2, 3, then that would be 3 rows, 2 columns, so that would be a 3 by 2 matrix. And you can talk about any entry in a matrix. So if we say this is equal to A and let's just say this is B, you would use the lowercase letter a and say, for example, 1, 1. And that'll give you this element right here, 0. You can say b of 2, 1, and that'll be second row, first column, which will give you 9. And some special matrices are the identity matrix, which is basically a set of ones and zeros. Some of the elements are ones and others are zeros. And basically, how you find an identity matrix of a specific dimension is, first of all, it must be a square matrix, which basically means that it has the same number of rows as columns. And all of the numbers in the main diagonal, which is this, must be ones. So let's say it's 1, 2, 3, 4, 5, 6, 6 rows by 6 columns. Everything else is a 0. So as I fill this out, the identity matrix is A, remember? Or I. A was the matrix we talked about earlier. It couldn't basically be anything, but I is the identity matrix, and it's I sub 6 because it's 6 rows and 6 columns. A 0 matrix, on the other hand, is just all zeros. So if I just make it 0, 0, 0, 0, it's 0, 2 by 2, which is equal to 0, 0, 0, 0. And it doesn't have to be a square matrix. It can be a 2 by 3. You'd make it 0, 2 by 3. And then we have operations with matrices. You can add and subtract matrices. And that is similar to as you would expect if you have 1, 0 plus 5, 6. You would add them up, each element by each element. So 1 plus 5 is 6. 0 plus 6 is 6. And there's a little caveat here, and it's that you can only add matrices with the same dimensions. This is 2 by 1, and this is 2 by 1. So the result would be 2 by 1. But you can't add it to a 2 by 2 matrix. It has to be 2 by 1 with a 2 by 1. You can subtract in the same way as well. When you're subtracting from the 0 matrix, that would basically be finding the negative of it. Speaking of which, we can multiply by scalars. The -1 times a matrix is multiplying by a scalar, so similarly we have 3 times 1, 0. Just as we did with vectors, you do 3 times 1, which is 3, and then 3 times 0, which is 0. In fact, we actually used a similar example when we talked about vectors. 3 times the I vector, or the horizontal component, which is 1, 0, which will give you 3, 0. In this case, it's 3, 0 as a matrix. Moving on to multiplication, matrices you can multiply, but it's a bit different because with addition it has to be the same dimensions, but with multiplication there's a different rule. So if I have 0, 1, 5, -1, 6, 11 times 3, 0, 4. I can actually multiply these because this is 2 rows by 3 columns. This is 3 rows by 1 column. So the pattern here is that the number of columns in the previous one should have the same number of rows as the next one. So 3 and 3 match, so you can multiply them. And the result is going to be a 2 by 1 matrix. So the inners have to match, and the outers would be the dimensions of the result. How you would multiply them is basically, think of tipping it over a little bit. So you're basically tipping this over and multiplying each element by a consecutive element. So you do 0 times 3, which will give you 0. And then you do 1 times 0, again 0. And then you do 5 times 4, which will give you 20. You add all 3 of these up, and that'll be your first element. Then you do negative 1 times 3, which will give you negative 3. You do 6 times 0, which will give you 0. And then you do 11 times 4, which will give you 44. And then simplifying it, you get 0 plus 0 plus 20, which gives you 20, negative 3 plus 0 plus 44, which will give you 41. That would be your product. And that's all there is to matrix multiplication. Just remember the rule that the inners have to match and the outers will be the dimensions. There's a few more things you can do with matrices that are unique to matrices. You can't really do them with vectors, for example. You can find the determinant and the inverse of a square matrix. And we're going to only consider 2 by 2 matrices because 3 by 3, there are different formulas that are harder to memorize, so using a calculator for those would be optimal. For a 2 by 2 matrix, let's consider a generic matrix 6, 1, 5, 3. The determinant of the matrix is basically going to be, on this diagonal, you multiply everything, subtract it from everything on this diagonal. So 6 times 3 would be 18. 5 times 1 would be 5. So you do 18 minus 5, which will give you 13. That would be your determinant for a 2 by 2 matrix. It doesn't work the same with 3 by 3 or any other matrix, and it's only for square matrices. Now the inverse of a matrix would be using the determinant. So let's call this A. The determinant of A, which is basically in absolute value symbols, the determinant of A is 13. So the inverse of A is going to be 1 over the determinant of A times, and here's where it gets a bit tricky. Let's say A is some matrix A, B, C, D. You're going to have to switch the places of some of the elements. So you do D is up here, A is down here, and then instead of switching B and C, you just take the negatives of them. So it'll be negative B and negative C. So in this case, we already found out that the determinant would be 13, and switching these places, we'd get 3 up here, 6 down here, negative 1 and negative 5. And now it's like multiplying by a scalar. We get 3 over 13, negative 1 over 13, negative 5 over 13, and 6 over 13. That would be your inverse. And one more thing to do with operations. When you're multiplying by the identity matrix, you're going to get the same matrix. That's why it's called the identity matrix. Like how 1 is the identity number or the multiplicative identity, because when you multiply it by any number, you get that same number itself. And that's all there is to operations with matrices. Now, there are a few applications that we should talk about. The first one is finding the area of a triangle using matrices. There are a couple of ways, but if you're given the vertices, let's say 2, 1, 7, 6, and negative 3, 4, you would basically create a 3 by 3 matrix. So the first 2 columns would be the coordinates. So you have 2, 1. 7, 6, -3, 4. And the third column would just be ones. Just fill it up with ones. Now you find the determinant of this matrix, and then you divide it by 2. So absolute value of A divided by 2. And you find the determinant, but you actually take the absolute value of that determinant because you always need the area to be positive. So it looks like double absolute value signs, but this is the determinant of A and the absolute value of that. Now, since it's the determinant for a 3 by 3 matrix, you're going to need a calculator. But there's actually a shortcut that's not really taught that much, but it could save a lot of time, especially if you're not allowed to use a calculator on a problem. You do a similar thing, except you find the vector going from one point to another point, and the first point to a third point. So from 2 to 7 is 5. From 1 to 6 is also 5. So that's your first vector. The second vector is from 2 to -3, so that's -5. And from 1 to 4 is 3. And you write a 2 by 2 matrix with the first vector as the first row, so 5, 5. And the second vector as the second row, so -5, 3. And now it's just a 2 by 2 matrix. You find the determinant, I'm going to call this B. You find the determinant of this, take the absolute value of that, divided by 2. So it's the same exact formula, except you have to do it with a 2 by 2 matrix. So plugging it into a calculator may be easier for you, but if you want something quick that you can just show your work on a quick piece of paper, no calculator needed, this trick is for you. And one more application, that would be solving systems of equations using matrices. First, let's see how to convert a system of equations into matrices. Let's say you have something like 2x plus 3y is equal to 6, and x minus y is equal to 5. Now you can use substitution or elimination to solve this. You can even graph it if you want. I guess you could guess and check, but that's not really recommended. But you can also convert it into a matrix equation. So you just take the coefficients, 2, 3, and in the bottom one here, 1, -1. That's your matrix A. Now your second matrix is just x comma y, sorry, x in the first row and y in the second row. And this is your matrix X. And this is equal to your coefficients 6 and 5. Or constants, I mean. These are your coefficients, these are your constants, and this is your matrix B. So if you were to perform the matrix multiplication, you would get 2 times x plus 3 times y is equal to 6. Very good. 1 times x plus -1 times y is equal to 5. Very good. But how does this help? Well, you can write this as a times x is equal to b. And here we run into something that relates to matrix multiplication, but I saved it for this time so we can talk about it when we're doing systems of equations. So matrix multiplication is not commutative. Normal multiplication with scalars is, but matrix multiplication isn't. And the reason why is because, for example, you have a 2 by 3 matrix and a 3 by 2 matrix. If you were to invert the order in this case, it would work because 3 by 2 first, the 2 and the 2 match, which works. But if you were to have a 3 by 1 matrix, this would become a 3 by 1 over here, and the 1 and 2 do not match. But in this case, the 3 and 3 do. So multiplying it this way works, but multiplying it this way does not. Which is why matrix multiplication is not commutative most of the time. And in this case, it wouldn't be because it's 2 by 2 and 2 by 1. So if you were to invert it, it'll become 2 by 1 by 2 by 2. 1 and 2 do not match, and therefore, in this case, it's not commutative. So what do? Well, we can basically divide both sides by a, divide in quotation marks. We can't really divide by matrices, but you can basically multiply both sides by the inverse of a. So it would become a inverse times b, because multiplying by the a inverse just becomes the identity matrix, and it just becomes like 1, you can ignore basically. And this becomes a inverse times b. Remember the order, it matters. And if you were to solve this, you would get your answer. So this might be a messy solution. So you can check it using elimination and using matrices. First of all, the inverse would be 1 over the determinant. So negative 1 times 2 is negative 2, minus 3 times 1 is 3, so it'll become negative 5. Then you switch the order, it'll become negative 1 here, 2 here, negative 3, negative 1. And this times 6, 5. So usually when you're finding the inverse, you would just multiply the coefficient, the scalar 1 over negative 5 by each number in the matrix. But in this case, first multiply the two matrices because it becomes easier, because then you'll get a fraction in the matrix, and multiplying by that would be messy, to say the least. So first multiply these two matrices. You'll get negative 1 times 6, which is negative 6, plus negative 3 times 5, which would be negative 15. Negative 1 times 6, negative 6. 2 times 10, 2 times 5 is 10. And this would simplify down to negative 21, 4. And when you multiply it by 1 over negative 5, it would become 21 over 5. The negatives cancel off. And this was 4, so it'll become negative 4 over 5. And you can simplify to decimals as well. But that's what your x and y value would be. That's basically it for matrices, because we covered what a matrix is, some of the special matrices, operations with matrices, and now solving systems of equations with matrices. So that's it for our next honors pre-calculus video. See you next time.